This is Daniel Coosbury, and having looked at the definition of random variables and probability distributions, this video is going to focus on a special kind of discrete random variable called the binomial distribution, and then we'll look at some of its applications to real-world problems. The binomial distribution describes the probability of obtaining exactly x successes in a sequence of n identical experiments. The probability, or the success probability for each trial is given by the number p. So imagine doing the same experiment over and over again where you're counting the number of successes as opposed to failures. So sometimes this is called a success-failure experiment. And what makes it binomial is that each trial has the same probability of success. So you could have a bunch of different things happen with each trial, but only one thing needs to be identified as a success, whereas the other things have to be lumped into the failure category. So if we can describe something as a success-failure experiment under some conditions we'll look at in a sec, it's going to be called a binomial distribution. The prefix bi refers to two. The two things are going to be success and failure. Okay, so here's some examples. We're going to flip a fair coin 10 times. So you see there's n experiments. There are 10 times, 10 experiments. We're going to describe a success for each coin toss as the coin landing on heads. And x is going to count the number of heads. Our success probability for each toss is going to be 1/2, which is normal, typical, fair, which is 0.5. So this is a binomial experiment because we've got the same thing going on over and over again, and we can count the number of successes, and we know the success probability. Here's another one. We know on average that 1 in 20 people who order a hamburger at a restaurant are going to receive a coupon for a free milkshake. 200 people order a hamburger in a given day, and we want to count the number of people who win a coupon. Our success probability is going to be 1 out of 20, which is this number, 0.05. So this is also a binomial experiment because we have a success, you win a milkshake. A failure is going to be you don't win a milkshake. We know your chance of success, and we also know the number of times this experiment is going to happen. Namely, this experiment is going to happen 200 times because 200 people are going to order it. And each one's either going to succeed or fail, and it's completely random. This is their chance of succeeding. So that's a binomial experiment. The conditions for the binomial distribution are as follows. So we're going to use this notation to represent the number of trials. So the n is going to represent the number of times we do it. P is going to represent the chance of success. And these are the 5 conditions that make something binomial. So you start with a fixed number of trials. So you have to know what n is. If you do something over and over again without n, it can't be binomial. You have to stop at some point and know what that number is to begin with, or it's not binomial. You have 2 possible outcomes, success and failure. Of course, these are going to take on other names, but like it's this or that, one or the other, only 2 outcomes. That's where the prefix bi comes in. The probability of success is the same for each trial. So this is important. Your success probability has to be the same for each trial. The trials have to be independent. This is important. So the outcome of one trial can't affect the likelihood of the outcome of the other trial. And the random variable x is going to count the number of successes. So whatever x counts is going to be considered successes, not anything else, namely failures. We're going to count successes. So those are the 5 conditions for a binomial distribution. If all 5 of those are true, then we have something binomial. So I'm going to look at a few examples and see if I can check these 5 conditions and make sure we have something binomial. What's nice is when you check the conditions, you often learn a lot about the experiment. And for example, I'll show you, we can identify what n and p are and use them to do problems. So we're going to call this is the toss a fair coin 10 times. I think I did that a few times. We're going to let x count the number of times that coin lands on heads. And is this a binomial experiment? So the first thing we should do is there a fixed number of trials? And the answer is yes. The number of trials is 10, so that's good. The second condition was, is there a success and failure? And yes, the success is going to be heads. The failure is going to be tails. I'm going to go down and do number 5 because we just talked about success and failure. X is going to count the number of successes, which is how we know the successes is heads. X is counting the number of heads. So that's how we know success is heads, failure is tails. So this is true, this is true. The next question is the success probability the same? And if we can identify the probability of success for each trial and it's the same, then we're okay. The probability of success for each trial is going to be, well, it's a fair coin, and the chance of getting a heads each time is going to be 1/2. So yeah, P is equal to 1/2 or 0.5. N is equal to 10. So when checking these conditions, we've identified what N is, we've identified what P is. We've also identified what a success is. A success is going to be H, heads. And then, are these trials independent? Are coin flips, fair coin flips, independent? Meaning, does one, if you get heads the first time, does it affect your chance of heads the second time? No, it doesn't. So that makes these independent. So that's good. That's good. This is binomial. Okay, so we got to check all those conditions to determine if something's binomial. I'm going to show you another example, and we're going to check the conditions and see if something doesn't work. So we've got 5 basketball players. They're each going to attempt a free throw. Let X be the number of free throws made. Is this binomial? Okay, so let's start by counting the number of trials. Number of trials is denoted by N. We have 5 people each throwing 1 free throw, so I think that's 5 trials. So we got a fixed number of trials. That's good. Do we have a success and a failure? Success. A success, I think X is counting the number of free throws made. So how about we say make a basket? And a failure is going to be to not make a basket or you miss. And what makes this binomial is it's either going to be this or this. So you're either going to make the basket or you're going to miss the basket. So that's good. There's nothing else that can happen. 3, let's do the success probability. Can we identify the success probability? I don't think we can, which is an issue. But what this is really asking is the success probability the same for each trial? Meaning, does the chance that one player make a free throw, is that the same as the chance that another player makes a free throw? And I don't think it is. So you've got 5 basketball players on a team, and each basketball player is at a different skill level. So I think we keep a stat of a bunch of things in basketball, including the number of free throws made or the proportion of free throws made. And I think, like, if you're shooting free throws, your proportion of free throws made is different than my proportion. You know, you may get half the free throws. I may get a quarter of my free throws. I can't identify a single P that applies to all 5 players because each player's P is going to be different. So I can't say that the success probability is the same. Unlike the coin flip or the people going in to get a burger and win a coupon thing, like the success probabilities aren't the same, which means this cannot be binomial. So like I said, all 5 conditions need to hold for it to be binomial. Here, we don't have a success probability that's the same. We just don't. All 5 players have different probabilities. This can't be a binomial. I'm not going to check the other things because I already got my answer. It's not binomial. Let's look at another one. We got 10 cards in a box. 5 of them are red, 5 of them are green. 3 of the cards are drawn at random. Let X be the number of red cards drawn. Is this a binomial experiment? All right, I've got 10 cards. I'm drawing 3. So if I'm only drawing 3 and I'm counting the number of red cards, I think my N is going to be 3. So I'm going to draw 3 cards. They're either going to be red or they're going to be not red, or red or green. I'm sorry, that should be a 2. So I can identify my success as drawing a red card. So each one of these that is red would be a success. My failures would be drawing a green card. There's only 2 kinds of cards. So I'm sorry, there are only 2 kinds of cards, red and green. So we're okay here. Now let's see. Probability of success. And I've got 10 cards in a box. So let's see. My chance of drawing a red card the first time is going to be, if there's 5 and 5, it's going to be 1/2. So my chance of drawing a red card the first time is going to be 1/2. 5 out of 10, or 1 over 2. Let me write that again as 5 over. I'll write that as 5 over 2. I'm 5 over 10. Okay. What's not clear in this problem is if I'm putting the red card back or not. So let's assume that I don't put the red card back. So I'm doing, I'll do it without replacement. So if I don't put the red card back, then I've only got 4 red cards in there and 5 green cards. My chance of drawing a second red card is going to be 4 out of 9 because there's only 4 red cards left and there's 9 cards left total. And you see how these aren't the same. These aren't the same. And if they're not the same, I don't have a binomial experiment. So just like the last problem with the basketball players, I need all of my success probabilities to be the same. So this is not binomial if we don't put the card back. So without replacement, we have something that's not binomial. This was good, but these probabilities ended up not being the same, and we needed them to be the same. Now let's imagine, because it's not clear in this problem, let's imagine that we do replace the card. Then the chance that I pull one out the first time is going to be 5 over 10. Then I'm going to put it back so that I have 5 red cards and 5 green cards again. The chance I pull a second red card out is going to be 5 over 10 because I put the card back. There's 5 red cards out of 10 total ones. The chance I draw it a third time is also going to be 5 over 10 because I'm putting the cards back. I'm replacing them, which would mean if I put these cards back, then this is good. You see how that's true? My success probability is P equals 1/2 or 5 over 10 if I put the cards back. If I don't put the cards back, then my probabilities keep changing every time I pull one out, and it wouldn't be a binomial experiment. So let's assume that I'm replacing the cards now and try to finish this. Are these independent? Are these draws independent? Are the trials independent? And the answer is yeah. If I'm putting it back, they are independent. If I'm putting the cards back. Remember, with replacement and independent go together. Without replacement means it's not independent, so that wouldn't work. But of course, we know without replacement, it's not going to be binomial anyway. And then we have X counts the number of successes. Yeah, so number of reds. So what we've just decided is, so this is good. This is good. What we've just decided is this is binomial if you put the red card back. If you keep the red card and keep drawing, you no longer have a binomial experiment because these probabilities keep changing. Your draws would not be independent. They would be dependent. And we know that from some of those pulling the ball out of a bucket problem. So this is an interesting one. But as you can see, we can check all 5. Assuming you put the card back in the deck and shuffle it, you've got independent draws. And you got a binomial experiment. Okay, so once we know we have a binomial distribution, we have a nice little formula that'll help us find probabilities. So the reason for classifying something as binomial is because there are some nice formulas that we can use for anything that's binomial. So sometimes finding probabilities is really hard, but when you have a formula, it makes it less hard. So we have n in this formula. There's a little n. That's our number of trials. We have a p in this formula, which is our success probability. And then we have the x counts the number of successes. So anywhere you see an x, this is the number of successes. And this works just like an f of x formula in algebra. You plug in an x, you put the x there, there, and there. Everywhere you see an n, this is the number of trials. And everywhere you see a p, you've got your success probability. So once you've identified something as binomial, you know what p is and you know what n is, and then you can find the probability that x is 0 or 1 or 2 or 3 or so on. I want to show you how to do this problem, or a problem like this using the formula. So we have a probability that a process produces a defective part being 0.2. And the probability distribution, then the probability distribution that x parts out of a sample of 10 will be defective follows a binomial distribution with n is equal to 10 and p is equal to 2. So what we're saying is you've got 10 parts, and out of those 10, the chance that any one of them is defective is 0.2. So each one has a 0.2 chance of being defective. I can draw a box around that. There's 10 total ones. So you can imagine the success would be, oh, it's not defective. The failure would be it's defective. And there's your, I'm sorry, we're going to have to change it so that this matches the P. So our success is going to be defective, which I know is backwards. But remember, this is our success probability. And our failure will be not defective. And we want to find the probability that 3 parts are defective. So the chance that 3 parts are defective, I'm going to plug things into this formula. You notice the C here, the combination we've done before. So N is 10, C is the big thing, C, we'll find that in the calculator. And then X is 3. So I'm putting a 3 there. And so this is all the ways I can pull 3 things out of a group of 10. And then little p is 0.2. This is to the 3rd power. So that's what that is. And then 1 minus p is going to be 1 minus 0.2, which is 0.8, but I'll write it like this, to the n minus x power, or to the 10 minus 3 power. Let me clean this up just a tiny bit. This is 10c3 times 0.2 to the 3rd times, this is 0.8 to the 7th power. So you can kind of see in this formula what we're doing. We're pulling out, if we have your 10 things, this is saying that 3 of them are defective with probability 0.2. That means the other 7 are not defective with probability 0.8. And this is all the different ways you can pull out a group of 3 parts from 10 total. Let's do this in the calculator. I'm going to do 10C3. Let me put this somewhere you can see. There we go. I'm going to do 10C3 in my calculator. So 10 math NCR 3. So that's 120. I'm going to do 0.2 to the 3rd in my calculator, just to show you what these numbers are. I'm going to do 0.8 to the 7th in my calculator. That's a really tiny number. So you see those 3 things? So if I do all that together, I'm going to do 120. Maybe I should do it like this, times 0.2 to the 3rd times 0.8 to the 7th. That should be the caret sign. So make that a little bigger so you can see what I did. Okay, so that's my 10C3, that's 0.2 to the 3rd, and that's 0.8 to the 7th. That's just me plugging in those things to my calculator. And I get 0.2013 for my answer. So 0.2013 is my answer. And that's using this formula. So this is stuff that, like, this is mathematics you know how to do now. You know how to find this number in the calculator. You know how to do 0.2 to the 3rd power. Use that caret symbol, the little thing that looks like this. And then you know how to do 0.8 to the 7th. Then you multiply them all together. You get this answer. So once you've identified something as binomial, like this defective part thing, all you need to know is what n is, what p is, and what x is to find these probabilities. And that's really nice. Another thing you can do, once you know things are binomial, you can find the mean and variance really easily. So there's a formula for the mean. It's like right here. There's a formula for the variance, and there's a formula for the x. Anything that's binomial is going to have an n and a p, and you're going to know what those 2 things are. You're going to know what the number of trials is and the success probability. So if you know those things, you can find the variance and the standard deviation and the mean using those 3 formulas. So I'm going to go ahead and do one very quickly and wrap this video up. I've got a probability that a new car of a certain model will require repairs during the warranty period being 0.15. A particular dealer sells 80 such cars. X is going to count the number of cars that will require repairs during the warranty period. Find the mean and standard deviation. So I know this is binomial because I've got 80 trials, and my success is going to be the requiring repairs, unfortunately. That's a success. And my probability that each one is going to require repairs is 0.15. I'm going to assume these trials are independent. It doesn't tell me it's independent. We're going to assume they're independent, and so that we could do this. So we have something binomial. My mean, then, of x is given by the formula n times p I showed you on the last slide, which is 80 times 0.15. which I'm going to do in my calculator as 80 times 0.15, and that is 12. So on average, 12 cars are going to need repair, or I would expect 12 cars to need repair. So you could call this the expected value or the mean. So when you produce 80 cars, you should expect 12 of them to need repairs. It could be more, it could be less, but you could expect 12. The standard deviation of x is given by the formula, the square root of the variance, which the variance is n times p times 1 minus p, and that's all under the square root. So this is the square root of 80 times p, 0.15, times 1 minus p, which is 0.85. Just did that, go mental math. So square root of 80 times 0.15 times 0.85. If you remember from a previous video, it took us a lot longer to find the mean and standard deviation. We had to put the whole distribution in the calculator to do it. Once you've identified something as binomial, you can find the mean and standard deviation using these formulas, and it's actually pretty easy because you're just using n and p. So this is 3.19. So once I know what n and p are, which I've identified them here and there they are, I can use these formulas to find the mean quickly if it's binomial. So an advantage to knowing something's binomial is you can find the mean and variation quickly. And I guess that's my point.